3.5, modeling with exponential and logarithmic functions. So instead of using our Glencoe textbook, or going back to that previous textbook, the Blitzer book, it just does a much better job with 3.5, and that's where your assignment's coming from also. So we start out with a formula that should remind you a lot of our A equals PERT, where we've got our continuous growth function. It's really the same thing. We have time, we have E. Instead of a rate, we have K. A naught is our initial amount, where P was the principal before. So there's not really a new formula to use. You could totally use this formula that we've been using in the past. They add in here how K is a rate of growth or decay. So if K is greater than 0, we have growth. If it's less than 0, we have decay. So exponential and growth decay models. So here is our first problem. In 1990, the population of Africa was 643 million. By 2000, so again, let's think about what's going on. This is going to be 10 years later. It had a population of 813 million. So if we're using that formula, and we can use either one, I prefer PERT on my own, but most of the time it freaks students out if we write a formula down and then change it on the next page. So I know that after 10 years, I have 813. So I'm going to write down that 813 is my amount here. My initial amount, that A naught, is 643. And this happens after 10 years. So I have e to the k times 10 power. So my whole goal here in problem A is it says use my exponential growth model to find a function that models the data. So when I have a function that models the data, I need to have an A, I need to have a number for A naught, E is good to go. I have to have a number for K and a number for T. So I have to find my initial amount and my growth or decay rate. So those are the two things I have to find. So they're telling me that initial amount, 643, but if I have to use all the information in the problem to find that growth or decay rate. So I'm plugging everything in, and now I'm going to have to solve for K. So I divide both sides by 643. And let's write, instead of K times 10, let's just write 10K. That's simpler. And just like before, if I need to get at that exponent, I can't solve unless that wasn't an exponent. I'm going to have to take a log on both sides because it's base E. I want to take a natural log on both sides. On the other side, we have the natural log of that fraction, 813 divided by 643. And so now on the right, we're left with 10K. It simplifies. We say cancels out kind of loosely, which is not really correct math language, but we all kind of understand that. And on the left, I have natural log of 813 divided by 643. And now I would have to divide both sides by 10. So 1/10 of the natural log of 813 divided by 643 is equal to K. And so K is approximately equal to, on my calculator, 0.023. So it's positive. I do have growth, and that matches the problem, right? I'm going from 643 million to 813 million. It's definitely growth. So we should not have a negative number here. So always kind of keep that number sense. So now I plug in numbers for A naught. So my initial amount was 643 million, and then E and my growth rate, 0.023. times T. So the idea now is I have a formula where if I plug in the number of years, I can get my current population out. So that's just like a y equals mx plus b, right? I know it looks like there's 3 variables, but E is not a variable. E is 2.718 being raised to a power. So now I have something that looks like a function. So in part B, we want to know when the population will reach 2,000 million or 2 billion. So I'm solving for time again. So I'm going to use that formula that we just had. And my current amount that I'm looking for, this was part A, now I'm on part B. I'm solving for my year, and right now my population is 2,000 million. So 2,000 is going to equal 643 times e to the 0.023 times t power. And I'm solving for t. So instead of putting in a number for t and making this easy, we have to solve with logarithms again. I will divide both sides by 643. Once you find out that this is really just applied equation solving like what we've been working on, but now we're applying it to a word problem, and the process is pretty much always the same, they get a lot easier. We're going to take a natural log on both sides because we need to get at the variable, which is in the exponent. And on the left, that gives us the natural log of this kind of giant ugly fraction. And it's really always something I want you to think about it here is that it's really like this ratio of my current amount to my initial amount, right? That's going to be important to the next problem. And then I'm always still thinking about calculator ready form, and I didn't make a big deal about that in the last one, but here was my calculator ready. Here was my value for k. Here was my function. I really had three important parts there. I know normally we do not like fractions inside fractions, but for my calculator ready on this side, I would write it like this. It's okay. You're going to plug it into a calculator anyway, but this gives me some sense of like, if you do screw up with your final answer, where did you screw up, right? If this is good, then I know you're having calculator issues, not comprehension issues in solving. So t should be about 49. And this was years after 1990. So 1990 plus 49 would be about let's see, 2039. So we're going to look at one more example. Next one's a little bit trickier. Let's see. So this one says we have, okay, strontium. I don't even know how to say that. Strontium 90. And they're talking about a half-life, right? It's decaying to half of the original amount after 28 years. So it really seems like we don't have enough information. We're trying to write an exponential decay model. So that's just like before, where we want to have all those numbers plugged in. We have a function, but it seems like we don't have enough. But we really do, because whatever our current amount is, so we're going to use this formula, and we're going to solve for k again. Our current amount is half of what I started with. So if I start with a naught, now I have half of whatever a naught is. So remember how I pointed out to you last time that we just really care about that ratio of the two. And that happens after 28 years. So if I divide both sides by a naught now, I have 1/2 of a naught divided by a naught. I just end up with 1/2. So hopefully you kind of saw that coming because I kept talking about the ratio. So 1/2 is going to equal e to the 28k power. So again, I can't get to my exponent. I need to take a log on both sides. So because this is a base of e raised to that power, we will take a natural log on both sides. Again, natural log is base e, so we talk about how these quote unquote cancel out. And then I have to take a natural log of 1/2 as well, right? We have to do it on both sides. So right now I have the natural log of 1/2 is 28k. Divide both sides by 28. This would be my calculator ready form. It is just fine like that. No need to simplify it. When I work all this out, this time I have negative 0.0248. I don't know why I kept 3 places on this. I just did. And it makes sense it's negative because we're talking about how this is decaying. I keep having after 28 years, I have half the amount left. So it's decaying, it's reducing. So now I need to write my function. This time I'm going to have more variables because it doesn't matter about how much I start with. I am always going to have this decay rate. So if I start out with 20 grams, I would put in 20, and then I would see what's left. So for part B, we are going to use our function that we came up with. So let's remember that and copy it down right away. A equals a naught e to the, already forgotten it, negative 0.0248 And after 60 grams, and we want to get this down to 10 grams. So let's just kind of think about this and just do some quick math. So if we start out with 60, after 28 years, we're down to half, which is 30. After another 28 years, we're down to 15. After another 28 years, we're down to 7.5, right? Every 28 years, that amount is dropping in half. So if we want to get this down to 10 grams, it's going to be somewhere between, let's see, 28 and 28 is 56. So more than 56 and less than 60, 84. So somewhere high 70s. So we just want to have kind of some number sense about this. So even though it's a completely unfamiliar thing, if we understand what half of it left means, then we can use some number sense. So, I almost did this backwards. We're not looking to have 60 left, are we? Just because 60 is bigger doesn't mean it goes there. So we're looking to have 10 grams left, and our initial amount was 60. Remember, we're decaying. So I have 10 equals 60 times e to the negative 0.0248 t power. So I'm going to divide both sides by 60. So I have 1/6 essentially. And same steps as the last time. We need to take a natural log on both sides. And so now all I'm left with is that exponent. And on the other side, I have still the natural log of 1/6. So my calculator ready form would be the natural log of 1/6 divided by that value of k. And that's going to equal t. And then when I plug it in, I get 72, approximately. We're just rounding to the nearest year. So about 72 years. So again, we use kind of some number sense to guess. I was thinking high 70s, but we use some number sense to figure out about what the answer should be. So we had our calculator ready form, lots of different parts to our answers on these. And on your test, I really need to see all of them. That is it for our 3-5 notes.